So good morning, everybody. Thanks for coming. So we have Professor Janusz Holyst from Warsaw University of Technology visiting us. He's a long-time collaborator of us. I mean, we have been working on several topics, and also we have shared several students. Christoph Sucheki, who most of you will probably remember. Also, Clement has some papers with Janusz. And the topics, for example, I mean, he's finishing a project on the propagation of emotions, called emotions. That is a European project, so how using Twitter data probably, how different moods are propagated between users. And he's here also in the context of another European project in collaboration with the IAC3, so this is the Institute for Advanced Computation and Communication Code, so it's directed by Carlos Bona and Tony Albona. And the project is called, it's a complicated one, Self-Organized Information Processing, Criticality and Emergence in Multi-Level Systems, that I think has another with another project that we also have here on multi-level.
Yes. This is from the same batch of projects.
So, thanks for the opportunity to listen to your talk.
Thank you, Victor, very much for inviting me here. I will talk about coupled networks. This is the plan of my talk. I will start with a short summary of what we have done together with Dr. Suchecki on coupled Ising networks. I have some nice simulation for this problem. And then I will come to the main topic, to the diffusion processes at coupled network. I'm stressing coupled network because, or multi-networks or systems of weakly coupled networks. So if we have a system of networks, we can generalize, for example, the Ising Hamiltonian, and everything is in this constant of interactions between different spins. And of course, this is magnetic spin acting at every magnetic field acting at every spin. If we have two networks, we can say that we have some interactions between spins belonging to the same network A, another interactions belonging to the network B, and the cross interactions if there are cross links between spins of different networks A and B. And in fact, it was the results of master physics of Dr. Suchecki when we shown that there's an interesting first order phase transition in such a system when the networks are coupled. When they are weakly coupled, it means this interaction constant between the networks is much smaller as compared to the interaction constant inside the network. I will demonstrate you a little bit from this effect at simulation. I hope it will work. So this now we have a system of two networks. I would call it a yellow network because there are yellow links between the nodes of this network, and this I will call a green network because green links between nodes of this network. At the moment, these networks are separated one from another. This is a smaller network, but with a larger number of links, of internal links. This is a little bit larger network, but with a smaller number of these green links. And these are the Ising networks described by the Hamiltonian that I showed at the previous slide. And we can use the Metropolis algorithm to simulate dynamics of the system. And these colors, red and blue, correspond to spin up and spin down. So at the moment, this network is polarized, let us say, nearly all spins up, and here majority of spins down. And if we start the simulation, you can observe here both changes of spins in both networks, and here are the mean magnetizations in this yellow network and in this green network. So you see this smaller network keeps its order parameter at nearly the same value, and we have larger fluctuations here in this larger network. Both networks are in the thermal bath of the same temperature. They possess the same internal coupling. Well, as I said, at the moment we have complete separation of those networks. And I developed this model. I asked Krzysztof to work on this model because I was always interested in so-called social dynamics. So imagine this corresponds to social communities. So there are different two communities that at the moment are completely separated. And in one community we have the red opinion. Majority of members share the red opinion. From time to time there's a small fluctuation. And in another network we have a blue opinion. Yes?
The temperature of the two networks is the same?
It's the same. And what is interesting, you see here the larger fluctuations, although we have the same. Why? Because the density of couplings here is smaller. Because here you can see we have 50 nodes, but on about 94 links, and here you have 30 nodes, but 158 links. And for complex network, okay, I'm not saying this is the complex net, this is not the crystal, this is not the. So the transition from a ferromagnetic state to the paramagnetic one depends on the density of links. So in some sense also on the size, because if you consider the Barabashi, okay, but it's okay.
The coupling in each layer I see, but how is the coupling across the layers?
At the moment there are no coupling at all.
No coupling.
At the moment, because as I said, so we have two social groups, imagine, and one is a red opinion, another is majority is a blue opinion. And now I will ask you if these groups start to interact. If I introduce crosslinks, who will be the winner of this competition regarding which of these opinions would be the unique opinion of the total system? The opinion of this group which is smaller, or the opinion of this group which is larger? Who of you thinks that will be the smaller group who will be the winner? You're the small. Why? Why do you think it will be the small?
Because it has the larger strength of links.
It is
the larger number of links.
The larger number of links. Yes, you are right. So statistically, you are right, and we can now try to perform this experiment. So I introduce cross links. So there are random cross links now introduced. I think we need to wait. It should be probably enough of these cross links, but since they're random, I'm never sure what is the. Oh yes, we are very close to separatics. Oh, yes, yeah. Well, so we found that we observed that it was that smaller group that was the winner, and you are right, it is the density of the links inside the group that was responsible for the result of this competition. And you saw also there's a jump, this continuous transition. Well, but whether it's simulations due to the finite size effect or due to the real thermodynamical calculation is another issue. But I would like to ask you now the following question. Imagine we cannot see this picture and we observe only this picture. Because if we are working in social science, we are not in position to see all contacts between the people, to measure all links in the community. Sometimes we can see, however, how the community in total react in time, in the class of time. So imagine we have only this picture. Can we forecast the outcome of competition observing only this part of system trajectory? Yes?
Looking at the fluctuations.
Yes. Looking at the fluctuation. So this system, where the fluctuation is larger, possesses also, using now the language of statistical physics, the larger susceptibility. So because this is closer to the critical point, and the critical point for this network is some temperature which is lower as compared to this. So it means also, using the concept of fluctuation dissipation theorem, the response of this system will be larger because fluctuations were also in the response the response to the external change of the environment. What is the change of the environment? This is the coupling to the second network. So coupling is symmetrical. However, the same coupling makes different effect for this and for that. But if we have already such a group, that we know that it can win this competition, we can now make the following experiment. We can try to change opinion of few influential members of this yellow group. Oh, maybe it's enough. This. So now I will introduce, using the language of physics, a local field acting at few members, at local fields acting at 5 members of this group. The field will be blue in the negative, let's say, direction. So the field is acting only on this 5 members, 5 because, 6. If the field is large enough, well, then these 5 people immediately converted the whole group to their opinion. And then this group converted the opinion of the larger group. So it means that influential politicians changing opinions in some community can in fact have a large impact on the whole society, or even on another society. And this is the effect. So I changed opinions. Using this field of the most influential, of the most linked nodes in this community. Well, So just to summarize, a weakly coupled network, we can definitely find some modulus, offered us possibility to observe discontinuous transitions of both order parameters. We can also observe the transition to the paramagnetic state. Details are given in the papers that I already cited. So let me now come to the diffusion process.
Problem.
Well, so let us assume a random walk at some graph. In the first approximation, let us consider the graph is a tree, and the graph consists of some number of nodes, and we have particles that can diffuse this graph. Let us, for simplicity, let us assume that these particles do not influence one another, so we can consider a single particle and then sum the effect of trajectories of all particles. So if the particle was at the beginning in this node of the graph, then if there's nothing special in this graph, then are the equal probabilities that the particle could migrate to one of these four nearest neighbors, and from these nearest neighbors, there's a probability flow that the particle can move to another neighbors, and so on and so on. And this can be easily described using some Markov chain theory for a single particle, and I now consider a little bit more complex dynamics. I assume that we have not only a pure diffusion, not a simple graph, but also that every node of this graph possesses some attractivity. So imagine that depending on the node, it's a larger probability that the particle would like to jump to this node as to another one. This probability, this will be described by what I call the fitness function. Fitness factor is a positive value parameter defining how a node is attracting to diffusing particles. And then if Aij is a connectivity matrix, I can write the following equation for the transport of particles from any node K to any node I. It depends on the connectivity matrix, on the density of particles at the node K, and this is just a normalization constant of all attractiveness around the node K, and this must be multiplied by the attractiveness of the node I. And this equation, this is the basic equation for my diffusion. So diffusion including local attractiveness, local heterogeneity of my graph. And this equation can be completely solved. The stable distribution, it's ergodic distribution, the density of particles is given by this function, and this is proportional to the attractiveness of the node. This is the density at the node I. So this was already known, I think, something like 5 or 6 years ago. It depends on the structure of the graph. If we have no Fi if all Fi are equal to the constant. So the density of the particles is proportional to, for a given node, to this parameter Gi, where Gi is a sum of nearest neighbors, so all elements of the connectivity matrix around the node I. So the larger is the degree of a node, the larger is the density of particles in this node. And that solution was already found something like 5 or 6 years, or maybe it was rediscovered by statistical physicists, but for sure it was found by mathematicians 20 or 30 years ago. We physicists always rediscovered many things decades later. Well, now let us consider entropy of the system. So since we have a distribution of probabilities, distributions of densities, equilibrium distribution of particles, we can calculate standard entropy of this distribution. And after short algebra, we receive the following solution. So this is the entropy per particle, because I can consider at the moment that there are no interactions between the particles. It is interesting, this is the size of my network. So log m is if we have a complete graph where every node possesses the same degree, then the particles are uniformly distributed. And this would be the entropy of such a regular graph. It is the maximum entropy for the system. And this system in the brackets, it depends on the structure of the network. It depends on these fitness parameters, as well on the topology of my network, because it's also these Gi constants that depends on the degree of the node I. And one can show it is always the negative. So the topology, introducing some non-trivial topology, it makes lowering of the maximum entropy that is possible at all. Well, now consider the issue of weakly coupled networks. So some pictures are similar to the pictures for the Ising, but now we have no spins at all. We have diffusion. So we have another kind of dynamics. Important is that for the dynamics, we also have the objects where the density of links inside one network is much larger than the density of cross links between the networks. Both networks can be different. Maybe they are written as they are they are not the same as this picture. So they can be different from the sizes, from the distribution of degrees, and so on. So both these, now I would call subnetworks, possess some connectivity matrices. And there's also a connectivity matrix between these networks. This connectivity matrix between these matrices, I will assume it is a random matrix. So we have random connections between the networks, and we have a small number of these connections. So probability to create a connection between any node of this network to another node of the second network is very low. So this why I can say we have two objects that are well defined and are weakly interacting. Because if I connect every node of this network to every node of this network, I can not say that I have separated objects. Well, so this assumption that we have a weak coupling leads us in principle to the following form, that we need that the probability of coupling multiplied by the size of the network multiplied by the average fitness is much smaller comparing to this normalization constant of a given node. This is the same for every for both networks. So now I can think about what I really have. I have two objects that are well separated, and I have the diffusion process of particles in networks and between networks. So I have tried to separate both these processes, saying that since inside any of these two networks there's a lot of links, the process of diffusion is very fast. While between the networks, the process of diffusion is very slow because there are only a few cross-links. So I have two time scales that I can, of course, calculate using looking into the connectivity matrix. But for me, it's important I can separate time scales of both these processes. If I can separate the time scale, so let us assume that I'm interested in observation of cross diffusion between the networks. It means that in such a way, I can write the probability that a particle, the density, of particles at a given node of a network T in such a form that this is the total number of nodes in the network A multiplied by this stable equilibrium distribution in the network A that I presented to you at the previous slide. So this is already, since we have a fast diffusion inside the network, so the system runs to the equilibrium very fast, so it does not depend on time in this approximation. Why this will be changing in time. And using this approximation, now I can reduce the system as follows. My original system consists of two networks with some cross links. I can now think on the system as follows. I have two objects. I have some interactions inside this object, and so I have flows of particles between these two objects. I'm saying I have interactions inside the object since this is this fast diffusion that I described at the previous slides. So in this way, when I can separate timescales, all equations will be much simpler as compared to the original equation for the total system of two coupled networks. Because now, after some algebra, I can write a simple equation for the total number of particles in the network A at next time step. It will depend on the numbers of particles in this network at the previous time step and on the number of particles in the net of the second network, where these are interactions coefficients between the networks. And I am able to calculate the efficient interactions coefficient between these networks. This is this awful formula, but I will show you a simpler interpretation of this formula at the next slide. This interaction coefficient can be simplified provided we have no correlations between the degrees, the degrees of the nodes and the fitness parameters. And then the interaction coefficients between these networks can be written in such a way that have a very nice interpretation. It means the influence of the network, because this interaction coefficient describes, let us check here, if this equals to 0, there is no escape from the network A to the network B. So this will be when it is small, when this is small, provided that we have a large attractiveness, large mean attractiveness of nodes in the network A as compared to the attractiveness of nodes in the network B, and provided the internal degree in the network A is much larger as compared to mean degree of cross links between the networks. What is this? This is the probability that any node from the network is connected to another one, and this is the size of the network B. So this is the average number of cross links for the network A, because every node possesses the probability PC to be connected to another node from the second network. So this average leads to this product. It leads to the degree between the networks. So the interaction coefficient, I will repeat, provided we have no correlations between the topology and the fitness coefficients, the interaction coefficient is dependent on this ratio that we could expect, but also on the ratio between the external degrees and internal degrees. And our approximation means that this interaction coefficient, since our networks are weakly coupled, so this PC is very small, this interaction coefficient is also very small. And this interaction coefficient is non-symmetrical. It depends on these fitness factors. It depends also on the sizes of the network. If the second network is much larger, then it possesses a larger in total a possibility to attract particles from the smaller network. Now we can write the First Fick Law, and we can for the transport particles between the networks. I mean the changes, because if I come in from the discrete from equation discrete in time to the continuous time equation, the changes in the total number of particles in the node in the first lattice depends on these two factors. It depends on the difference between the total number of particles in both networks multiplied by some constant that is a mean value of this interaction constant. And this constant plays a role of a diffusion constant between the networks, plus some force that exists if there's asymmetry between the networks. You can see even if the number of particles in both networks are the same, this constant, this force will pump the particles from one network to another if these interaction coefficients are unsymmetrical. If one of the networks, the mean attractiveness is larger compared to the second one, or if the sizes of the networks are different, or if the average internal degrees in both networks are different. In principle, if we have a large internal degree in the network, then the particles prefer to stay in this network rather to escape to the second one. So this constant decays with the internal degree of a network. So we see the effect of our approximation. The transport between the networks can be splitted to to the standard diffusion with well-defined diffusion constant, and to the pumping force, which is the effect of non-equilibrium between the network topologies and this fitness factor. What about now entropy? Now if we calculate the entropy as a function of time, taking into account this distribution of that I showed at the previous slide, we see that the total entropy now consists of the following terms. Excuse me. So the interesting is production of the entropy, so the derivative of this formula at the time. So we see the entropy production is due to two effects. This is, of course, the entropy is produced only if the system is not in the equilibrium. And it is, so if this is not equal to 0, if there are non-equal entropies in both networks and local entropies per particle, then we have the, let us say, export from entropy from one network to the another. So this is the transport of entropy between the networks if they are they have possessed different structures. Why this term is due to the fact that entropy is our lack of information regarding whether a single particle is in the second network or in the first one. So this equals to 0 if we have the same numbers of particles in the same in both networks. So it would be the maximum of the entropy. This would be 0 if we have the same networks. So production of the entropy is combination of the effect of whether the particle is localized in one of the subnetworks and whether in these subnetworks the entropy for the particle is the same or not. And the entropy is changing due to these two terms. If we have not just two networks, if we have the system of networks, we can write all this equation in a more complex form. We can write now that the number of particles in a network A depends on the number of particles in all another networks and some interactions coefficient alpha, and I'm able to calculate this interaction coefficients. So I can have a diffusion in a multi-network system where interactions coefficients and the macroscopical scale are following from microscopical structure of both networks. So also let's say continuous in time equation can be written for the issue of system of networks. Now we have diffusion constants between different networks, and we have pumping forces between different subnetworks depending on the symmetry of the system. And the entropy production can be in principle written in such a way. It depends on the equilibrium entropy per particle in a given network minus a term related to the size, to the total number of particles in a given network. So in conclusion, I showed to you that diffusion process in weakly coupled connected networks can be well described provided that we use the concept of time scale separation. I took into account that one of subnetworks could be more attractive for particles than another. And if there is low density of cross links, this time scale separation can be performed. We received first Fick Law and the formula for entropy reduction. We received an equation for diffusion constant and equation for pumping force responsible for flows of particles where the system is not in equilibrium. And, well, the results are described in this preprint, and I hope they will be sent for publication very soon. I'm not sure how much time I had. It's not good. It's fine. Okay. Thank you.
So please, questions?
So maybe I didn't understand something correctly, but as far as I understood, why do you call them multi-networks? Because what I saw, they are just one network with different communities, with different...
Well, the definition of multi-network is not unique. I would say that this is the system of networks, of weakly coupled subnetworks.
So there is no difference with one network which has some community structure?
Well, the issue is that I need some small parameter. The parameter is defined as the ratio between internal degree and external degree, or external degree to the internal degree. This was this parameter PC. If PC is equal to 0, I have completely separated community. If PC is 1, I cannot say that I have any community structure. If PC is much smaller than 1, I can use my approximation.
Okay, this goes to another question, because maybe I didn't understand again something really, but I think you can do the approximation even if PC is 1. Just it doesn't have so much sense. But you could have a complete network and say, I just look at half of the network and half of the other network, and I apply this, and this would still apply.
Yes, yes and no. I can write equations for the computer simulation for any value of PC, but the theory needs this approximation of timescale separation. It means that I do not consider the process of relaxation inside the network. I assume that it is so fast that the network seen for the second one is one compact object. So approximation, if I would like to write the total equation of motion, I had this G function, which was the sum over all of all fitness parameters around any node. Then I had to take into account also the fitness parameters coming from the second network. If this contributions from the second network is comparable to the first one, my denominator in some equation will be changing from node to node, and I could not find the solution of this equation, mathematically speaking.
Yes, what do you mean by when you say weak coupling of the network? Is it just the number of links or also the weight or the...
This is an unweighted network. So one can extend this concept, and it is done partially in our preprint.
So if you have two networks, then it's just the number of links?
Yes, the number, if you would like to have a weighted network, you need to say, okay, that the weights of the crosslinks are much smaller corresponding. Yes.
Yeah, okay. And can you, when you have a hierarchy of networks, can you have more steps? Like, can you have...
We are just working. Yes. We are just working on a compact form to make it for many hierarchies. Yes, that we are starting. We have clusters of clusters and so on. We are just working about this. Yes. Then we have the operator coming from one level to the second one.
You're always looking at the symmetric random
have you...
Well, this is not completely symmetric because we have this fitness factor.
Yes, but you have some relaxation to a distribution function which is an equilibrium one.
But this equilibrium is dependent on the fitness function.
If you have directed flows, does it completely break down, or can you still use? Do you know what remains of the theory system?
Well, in so we can not. So we need to have symmetrical connectivity matrix. This AIK. So for our calculation, so I cannot use completely directed network. I can simulate some effects of asymmetry between the nodes by these fitness factors, and this is the reason that we introduce them. Because if one node possesses the large fitness factor and the second one extremely small, then in some sense this is one direction of the diffusion between these two nodes.
But this is a gradient type of.
The
assumption of separation of time scale is essentially the assumption of local equilibrium. So you have two systems in local equilibrium.
Yes, precisely.
You are describing the approach to global
Yes,
equilibrium.
yes, exactly.
In the next step would be to analyze to put some gradient, some flows on it, like in non-equilibrium thermodynamics, you put weakly a flux in thermodynamics, a flux of temperature or particles. It will be something like a diffusion flux in one of the things.
But this was done. But I had the fluxes of.
No, but finally you approach to equilibrium. I mean,
yes,
like
but
steady states. Can you find non-equilibrium steady states here?
I can find the way the system runs towards equilibrium, because these are the equations for the total number of particles in the network of the one of the network, how they change in time. By they change, they run to the complete equilibrium where this equals to 0.
Okay. Yes, I was thinking that the analogy of this with thermodynamics, which then the next step is to find the linear relationship between the variables and the
Onsager
gradients involved.
And Onsager coefficients. Yes, I gave this task to one of my students, but he was not able to solve it. That's it.
So far.
Yeah, well, a bit because what Emilio said, I think that this formally can be mapped to a random walk on a directed weighted network, where the connectivity matrix is Aij Fi, and this is not symmetric because then it's not the same as Aji Fj, so it's directed and it's weighted because of the Fi.
So in some way, the effect of directness in the net is taken into account, but this is not equivalent to the direct, because in the directed network, my connectivity matrix is asymmetrical, and I need for this theory connectivity matrix to be symmetrical. I can introduce asymmetry in the nodes, not in the links. In the nodes, not in the links. And it means that I have not so many degrees of freedom, because you can ask, this is the same. But if I have some number of nodes, for example, m, so I have m parameters for the fitness of the nodes, but the number of links is much larger. It depends on the connectivity.
Yes.
So if I would like to have a network where I take into account that there are asymmetry at the link, I had used another set of parameters. Already from
Actually, you're doing that at more constraint.
it's more constraint. Yes. What you would like to do is a broader class that I'm not able to attack using this format. We wanted to do it, but we failed since we had to obey the relation of the symmetricity of this connectivity matrix. This can be not broken. We can break the local symmetry, but not the link symmetry.
So, I have one, equation 10 basically is telling you that the external links are much less than the internal links. But in order to derive the average connectivity, you have not used the precise degree distribution of the network, right? Have you?
Well, we did it. We performed this is the average degree in the network, in any of the network.
But what I mean is that this equation is in principle correct, irrespective of the shape of the degree distribution. Because
Yes.
I suppose that this is the matrix, and then my point is, if you have power law degree distribution, then you have a lot of nodes with low degree. So you could have for those more external links than internal.
Yes.
But on average, this equation is still fulfilled, right? Because on average, they are much lower. But that could change a lot the dynamics, right? Because locally, this is not fulfilled, so I suppose that the mixing is faster, and that could affect the overall dynamics.
But even for power law distribution, I have some minimal degree.
Yeah.
So it means we tested. You are completely right. We tested this for Barabashi-Albert. And for Barabashi-Albert, it meant that instead of this K, we had to put the smallest degree of a node.
Well, but this is a safe.
This is
a safe way of doing it.
This is the safe way. Yes. So in average, I can. So this is the parameter for the average, but all this is on an approximate kind of mean field approximation. To escape from fluctuations coming from the topology of the network, that some nodes possess low degree and it could be connected to many partners from the second, I have to put here the minimum value of a degree in a given network. And you are completely right. For Erdős-Rényi, it is just would be the fraction of the characteristic of parameters of Erdős-Rényi. Why for the Barabashi-Albert it would be it is the fraction between because I have Erdős-Rényi between the networks. On the other side, since I have Erdős-Rényi between the networks, the possibility that one node is connected to many nodes from the node is very small, because we have the Poissonian distribution with no heavy tail. So, but to be safe, I should consider here the minimum value of the interval.
Okay, so one last question? No? Well, thanks.